Imagine we want a satellite to take pictures of a particular spot on Earth. We will need to align the payload so it points at the spots, and we need to control the satellite's attitude so it points down toward Earth. In space terms, we say down toward Earth is the native direction. The opposite direction, away from Earth to the space, is the zenith direction. Before we can describe attitude, we must define a coordinate system. We define attitude in terms of angles instead of distances. Attitude is described as an angular rotation with respect to a body's central coordinate frame, called the body frame. For airplanes and vehicles like the space shuttle, the x direction points at the nose, the y direction points at the left wing, and the z direction will point out of the screen, following the right-hand rule. It is usually given as roll, pitch, and yaw angles, where roll is a rotation about the x-axis, pitch is a rotation about the y-axis, and yaw a rotation about the z-axis. A spinning mass has angular momentum, which is a function of its shape, mass distribution, and rate of spin. For example, a compact object with all the mass concentrated near the center of mass spins much easier than an object that has a lot of mass located far from the center of mass. This is why figure skaters bring their arms in to spin faster and extend their arms to slow down. By knowing the mass moment of inertia and the object's angular velocity, we can find its angular momentum. To change an object's momentum, we must apply a force. If we kick a football or hit a volleyball, it's easy to see that applying a force to an object changes its velocity. But how do we apply a force to a rotating object? If we push a rotating object like the one in the video, it starts moving in a straight line direction while continuing to spin. But what if we want to change the rate or direction of spin without moving it anywhere? Then we must apply a torque. A torque is a twisting force that results when we try to rotate an object, like when we use a wrench to turn a bolt. When an object has angular acceleration over time, it gains angular velocity. To determine a spacecraft's attitude described by an angle, we must look at how long it accelerates and how long it moves at some angular velocity. In other words, by applying a torque to a non-spinning free-floating object, such as a spacecraft, we create angular acceleration, leading to angular velocity and a change in angular position. The model for this aspect of spacecraft behavior is the block diagram. When we apply a torque to a non-spinning spacecraft, predictable things happen. But if the spacecraft is spinning when we apply the torque, the dynamics get more complicated. As we know, a spinning object has angular momentum. Applying a torque parallel to the angular momentum direction causes angular acceleration and angular velocity changes. However, applying the torque in a direction other than parallel to the angular momentum vector causes something quite different. In this figure, we have a spinning disk with a force couple applied to it. You might expect the mass to begin to rotate in the same direction you are torquing it. But that's not what happens. The mass begins to rotate counterclockwise about an axis that comes out of the page. This phenomenon is known as precession. There is one more important result of the interaction between a spinning spacecraft and an applied torque. We all know that spinning footballs and spinning rifle bullets travel faster and farther than non-spinning ones. This is because spin makes them more stable and resistant to outside torques. The faster they spin, the more stable they become. This stability is referred to as an object's gyroscopic stiffness or rigidity. So why cannot we just send a satellite out in space with a desired attitude and forget about it? Well, space can be a dangerous place. Over time, if we do nothing, environmental effects, disturbance torques will drive a spacecraft away from its original attitude. These torques are extremely small, but they can eventually rotate even very large spacecraft. We are concerned with four main sources of disturbance torques. The first one is the gravity gradient torque. This results from difference in gravitational force on different parts of a spacecraft. We remember that Newton said the force of gravity on an object varies inversely with the square of the distance from the central body. Imagine we have a spacecraft with a form like in the image. If the spacecraft is hanging vertically, the lower mass M1 will have a slightly greater gravitational force on it than the higher mass M2. If M2 is directly above M1, nothing will happen. However, if the spacecraft gets displaced vertically, this slight difference between both gravitational forces will create a torque at the spacecraft that will tend to restore it to the vertical. This is fine if you want it to be vertical, but otherwise you will have to fight against this torque. We can estimate the magnitude of this torque using this formula. We can see from this equation that the torque depends on the angle between x and the local vertical. The greater the angle, the greater the torque. Another source of disturbance torque for a spacecraft comes from the sun. The sun exerts a force called solar radiation pressure on exposed surface. We are used to being warmed by the sun, tanned by the sun, and even burned by the sun. But pushed by the sun? Yes. One way to think about light is as tiny packets of energy called photons. Photons are massless, but they do have momentum. The momentum of a photon is given by Einstein's relation, so we can write the momentum of a photon as photons strike any exposed surface, they transfer this momentum to the surface. So why can't we feel this force? Well, because this force is very, very small. We can estimate this force using this formula. The force exerted on even a very large spacecraft with, for example, 10 square meters of surface will be only 90 nanonewtons. Assuming this force acts at the center of pressure of the surface, and even with a 1 meter moment arm, the resulting torque will be still very small. But even this tiny force acting unevenly over different parts of the spacecraft, especially large areas like solar panels, can cause problems for a spacecraft needing precise pointing. The next source of disturbance torque comes from Earth's magnetic field. Because of the impact of charged particles in space, the surface of a spacecraft can develop a charge of its own, giving it a distinct dipole, north and south ends, like a compass. And like a compass needle, the dipole charged spacecraft will similarly try to rotate as it passes through the magnetic field. The last disturbance torque we have to worry about is drag. In low Earth orbit, the atmosphere applies a drag force to a vehicle. Because parts of a spacecraft may have different drag coefficients, drag forces on different parts of the spacecraft can also be different. This difference, along with the distance between the center of pressure and the center of mass, causes a drag torque. As we have seen, sensors are an essential part of control systems. Sensors are the control system's eyes and ears. They observe the system to determine attitude and transform these observations into signals that the controller processes. To understand how sensors help a spacecraft determine their attitude, imagine we are flying a spacecraft in low Earth orbit and we need to point the nose at some spot on the surface. Imagine that your seat is facing toward the nose. To point the nose at the surface, you must first determine where you're pointing now. How can you do this? The obvious answer is to look out of the window at some reference. Let's say you see the sun out the left window. Will this tell you all you need to know? Unfortunately, no. A single reference point gives you a current attitude in only 2 dimensions. In other words, you will know that the left wing is pointed at the sun and the nose is pointed perpendicular to the sun, but the nose could point in various directions and still be perpendicular to the sun. So what do? To determine your attitude in 3 dimensions, you need another reference. When pilots fly along in their airplanes, the easiest way for them to determine attitude is to look out of the window. If the ground is down and the sky is up, they are flying upright. Similarly, the simplest way for a spacecraft to determine its attitude is to look out of the window. To look at a subject, a remote sensing system must follow the next steps. When it comes to remote sensing for attitude determination, there are 3 main subjects available for reference. These are the Earth, the Sun, and the stars. In low Earth orbit, Earth fills a big portion of the sky. Earth sensors can indicate the down direction by simply discriminating where Earth is with respect to the rest of the sensor field of view. At geostationary orbit, the angular radius of Earth is very small, so to use Earth as a more accurate method of attitude determination, a sensor must focus only on one small part. Sensors can detect Earth's horizon by focusing on a narrow band of electromagnetic radiation emitted by carbon dioxide. Sun sensors are similar in function to Earth sensors. A sun sensor finds the sun and determines its direction with respect to the spacecraft body frame. Earth and sun sensors can give accurate information about attitude in only 2 dimensions. A more accurate 2-axis reference is a star sensor. Star sensors measure a spacecraft attitude with respect to known star locations. They compare these measurements to accurate maps of the brightest stars stored in the spacecraft memory, the angle between the known star's position and a reference axis on the spacecraft, then helps determine the spacecraft inertial attitude. By using 2 or more star sensors, the system can determine its attitude in 3 dimensions. Gyroscope can determine attitude and changes without needing to look out of the window. The simplest type of gyroscope is a spinning mass. 2 basic principles of gyros make them useful as attitude sensors. With no torques, their angular momentum is conserved, they always point the same direction, and with a torque applied, they process in a predictable direction and amount. When a mass starts to spin, its angular momentum vector remains stationary in inertial space. For example, let's spin a gyroscope at 6 a.m. with its angular momentum vector pointed at some convenient inertial reference. We can then observe how conservation of angular momentum works to keep the gyro always pointed in the same inertial direction. In this case, the angular momentum vector h appears to track a fixed point in inertial space. As the gyro sits in its stand, it looks like it's rotating throughout the day, but actually the stand is moving as Earth rotates, and the gyro remains stationary in inertial space. Museums often demonstrate this principle with huge pendulums suspended on long cables. The swinging pendulum's plane remains fixed in inertial space, but as Earth turns, the pendulum's path appears to move. After determining what the spacecraft's attitude is, we may need to change it. For example, to compensate a disturbance torque or rotate the spacecraft to point a new subject. Actuators provide the necessary torque to rotate a spacecraft. We can divide actuator types in 2 general classes, passive and active. Passive actuators operate more or less open loop. After the spacecraft is in desired attitude, passive actuators will keep it there with little torques needed or no additional torques needed. On the other hand, active actuators require continuous feedback and adjustment. The first passive actuator takes advantage of the gravity disturbance gradient torque discussed earlier. We can exploit this free torque to keep a spacecraft oriented in a vertical orientation. Fortunately, a spacecraft doesn't have to be shaped like a dumbbell to take advantage of this effect. For example, we have the moon. We can only see one side of the moon, right? And never the mysterious dark side. That is because the moon itself is in a gravity gradient stabilized attitude with respect to the Earth. For a pair of co-orbiting objects A and B, the gravitational force from object A, in this case the Earth, upon V, the Moon, will change with distance, being greatest at the nearest surface to A and least at the most distance. This creates a gravitational gradient across object V, in this case the Moon, that will distort its equilibrium shape, and the body of object B, the Moon, will become elongated along the axis oriented toward air. These elongated distortions are called tidal bulges, because these distortions are now displaced from the Earth-Moon axis. Earth's gravitational pull on the mass in them exerts a torque on the Moon, and the torque on the Earth-facing bulge acts to bring the Moon rotation in line with its orbital period. This phenomenon is known as tidal locking. Using this principle, a satellite can be stabilized. A spin-stabilized spacecraft takes advantage of the conservation of angular momentum to maintain a constant inertial orientation of one of its axes. Because the angular momentum vector of a spinning mass is fixed in space, the spacecraft tends to stay in the same inertial attitude. A good example is the Earth. The spinning Earth is essentially a gyroscope. The Earth's angular momentum vector points out of the North Pole. This vector stays fixed in inertial space. This vector points at the North Star, and that's why when we observe the motion of the stars at night, they all appear to rotate around one star. Spin stabilization is useful to point in the same inertial direction, but it is not for pointing the angular momentum vector at Earth. For that reason, it's mostly used during spacecraft deployment when the gyroscopic stiffness is useful to maintain orientation until the spacecraft is free from the launch vehicle. To avoid these limitations, we can use a dual spin system. These systems consist of two cylinders, one inner cylinder surrounded by an outer cylinder that is spinning at a high rate. This cylinder provides overall stability, and the inner cylinder rotates at a much slower rate. For example, if a spacecraft is in geostationary orbit, the inner cylinder will rotate at orbit rate once every 24 hours, keeping the sensors and antennas focused on Earth. We usually don't use a single type of attitude actuator alone. A damper is another actuator usually used in combination with others for a complete system. A damper is a device that changes angular momentum by absorbing energy. Attitude dampers use friction or other means to convert angular momentum energy into other forms. A common type consists essentially of a tube filled with viscous fluid and a mass attached to springs. The friction between the mass like a ball and the fluid in the tube converts some of the momentum into heat that slowly dissipates throughout the spacecraft. On the other hand, thrusters are the simplest type of active actuator. They are simple rockets, and by applying a balanced force with a pair of rockets on opposite direction of the spacecraft, on opposite side of the spacecraft, we can produce a torque that can rotate the spacecraft in any direction. Actuators that rely on angular momentum are the most common type used for spacecraft attitude control. Momentum exchange systems are used to control the attitude of a spacecraft without throwing consumable mass overboard, as occurs with the use of thrusters. In this image, we have a system with N flywheels, also called reaction wheels. They are attached to the body of the spacecraft at various locations. The total mass of the entire system is the vehicle's center of mass is G, through which pass the three axes of the vehicle's body fixed frame. The center of mass of each flywheel is connected to the spacecraft, but the wheel rotates independently. The body of the spacecraft has an angular velocity omega. The angular velocity of each wheel differs from that of the body of the spacecraft. The angular momentum of the entire system about the vehicle's center of mass G is the sum of the angular momentum of the individual components of the system. The first component is the total angular momentum of the rigid body, including the spacecraft and all the flywheel masses. The second element is the net angular momentum of the flywheels about each of their individual center of mass. We must emphasize that here the moment of inertia is not an scalar but a matrix, also an inertial tensor, that is fixed relative to the body frame, which means this matrix does not change with time. For no external torques, the following equation remains constant. If a reaction wheel spins faster, because the total momentum must stay constant, the spacecraft angular momentum must automatically decrease to compensate it. The vector increase in the reaction wheel's momentum must exactly equal the decrease in the spacecraft momentum to keep a constant total. To conserve momentum, the spacecraft must either slow its rotation or start rotating in the opposite direction. In either case, the spacecraft attitude has changed simply by spinning a small mass faster inside. Two reaction wheels can deliver precise control of spacecraft attitude in all three axes. Now let's take a look at a real example. The Hubble telescope combines several devices mentioned in this video to know, change, and maintain its attitude. It uses solar sensors to know its orientation with respect to the sun, star sensors to know where to point, magnetometers to know its orientation with respect to the magnetic field, gyros to know how and with which velocity it's moving, and finally reaction wheels to keep and change its attitude.